Hello, Allegheny College astronomy students, and welcome to another introductory astronomy lecture. Today we'll be recording the lecture for Friday, April 17th on dark matter, dark energy, and the fate of the universe. I like to start out with the astronomy picture of the day, and I chose one from 3 years ago that's going to be directly relevant to what we'll be talking about today. This is actually the bullet cluster, and there's a lot of different information on this image here to unpack. In the background you see visible light, and there are lots of galaxies in this vicinity, and in fact in the middle of the image you see these clusters of galaxies. There's a cluster over here of galaxies, there's another smaller cluster over here, and these clusters have passed through one another in the past. The way that we know that is by looking at some of the other information that's shown here. In blue and purple we see where the matter is, and that's as measured by this technique known as gravitational lensing that we'll be talking about today. And you can see that the matter has followed along with the galaxy clusters. It turns out most of that matter is going to be dark matter, not just the ordinary light emitting matter that you see in these clusters. And then here, this hot X-ray emitting region, you see how there's a shock front right here? You know how like a boat, as it goes through the water, you see this curve that comes around from the side of it, a bow shock? That is the same kind of shape you can see here. And the reason for that is as these clusters of galaxies passed through one another, the gas clouds that lie in between them would strike up against one another and get heated and slow down from the collision. But it looks to be the case that the matter of the clusters just moved right along, passing through one another. A hint that maybe dark matter is to help explain this. Down in the description below, they tell us that there are other alternative theories for how to explain this. Those involve modified Newtonian dynamics, MOND. But most astronomers, as we'll discuss today, believe that dark matter exists. Okay, so there's your chapter opening picture, and it turns out to be the same picture as that astronomy picture of the day that we were just talking about. So we won't say much more about that. Section 1, Chapter 18, Unseen Influences in the Cosmos. We want to start out by giving you a definition of what dark matter and dark energy are. These are two separate things that are often confused with one another by people who are just learning about the subject. So dark matter is, as the name implies, mass or matter that emits little or no light, but we can infer its existence by its gravitational influence on other things. And so things do gravitationally fall to dark matter, but you're not able to see it, and light will pass right through it. Dark energy is an unknown form of energy, and so it's not entirely understood. So in this case, the word dark here takes on a bit of a different meaning. It almost means like it's not certain or understood well what this energy is. And it is causing, though, we can see its effects. It's causing the accelerated expansion of the universe. Not just the expansion of the universe, but with time, it causes the universe to expand faster and faster and faster, which is counterintuitive and surprising. Here's a cartoon for you. These two scientists are working at the dark blank research unit, and one is saying to the other, "Henderson, I believe I'm onto something." Now, do you think that they are working at the Dark Matter Institute or the Dark Energy Institute? Go ahead and pause it if you need to. Well, the idea here is that you're not able to see the other scientist. And they're there, you can detect them by hearing what they're saying, but you're not able to see them. So this is much more like dark matter. They're working on the dark matter problem there at the Dark Matter Research Institute. Dark energy has to do with an anti-gravity term that's causing this accelerated expansion. None of that is related to us here in this particular comic. All right, section 2. we'll spend the rest of today's period talking about the evidence for dark matter. And to do that, we're going to want to first understand what we mean when we talk about a rotation curve. A rotation curve is going to have orbital speed on the vertical axis and a distance from the center on the horizontal axis. And so we'll take as an example our own solar system, which has the sun at the very center. And then there's Mercury, Venus, Earth, of course, is the third rock from the sun, Mars, and so on and so forth. And you remember from Kepler's laws that the closer a planet is, the faster it's going to be orbiting around. And we see that Mercury is moving the fastest, then Venus next, and so forth. So let's take a data point on Mercury. Here's its distance from the sun being represented on the graph, and here is its speed. Now if I click on Venus next, that's farther out, so we're further to the right here, and it's slower, so it's down. And we keep going. Earth, Mars, etc. The farther you get from the sun, the slower the planet is orbiting. And so that is the rotation curve data for our solar system. You could imagine putting a line between all of those dots, and that would be the particular curve. And this is how rotation curves work whenever you have the vast majority of the mass concentrated at the center, like in our own solar system. Okay, well, you may not always have the mass concentrated at the center. In fact, it's not at all that way in galaxies. Yes, it's true. There's a million or billion solar mass black hole at the centers of galaxies, but remember that these galaxies will have a trillion or more, or 10 to the 11 solar masses, 10 to the 12 solar masses in mass. And so the idea here is that that black hole mass, even though big, is small compared to the mass of the galaxy as a whole. And so it's not like in the solar system where all the mass is concentrated at the center. So what would the rotation curve for the Milky Way galaxy look like? Well, I'll go ahead and I'll click here in the center, and I get a data point for the rotation. When I'm close to the center, it looks like the orbital speed is a little more than 100 kilometers per second. And then I'll click again and again. And as I go outward, I actually see the trend being that the speed increases. So this is already different than in the solar system. Perhaps it's not surprising, because in the solar system, as you go out further, other than the occasional planet or asteroid that you pass, there's not additional mass inside of where you're orbiting to hold you in your orbit. And in this case, as you go out further and further in the galaxy, you pass many more stars and gas clouds and so on. And so that, in that sense, it's perhaps not surprising that the orbital speed is going up, because as you go up further, there's more stuff inside your orbit pulling you in, and so you would need a faster speed, or at least it seems reasonable you should need a faster speed to maintain that circular orbit. And so we'll keep going outward for a while, and we see that trend, still not surprising, and it starts to level off, and maybe even decrease a little bit as we get towards the outside. And you might say, okay, well, that's reasonable as well, because maybe I'm just not enclosing a lot more mass as I go out, and so it's going to start to transition to being more like the solar system, right? There are these two competing effects. As you go outward, you enclose more mass, but as you go outward, the strength of gravity, which falls off like 1 over r squared, where r is the distance to the center of the galaxy, that 1 over r squared is getting smaller. So those two competing effects, maybe that explains why it plateaus here and even possibly dips a little bit. But here's where it gets really surprising. Occasionally you see some gas cloud far outside of what otherwise is the visible disk of the galaxy, and you measure its orbital speed, and what do you find? You find that it's leveled off, right? Maybe some small oscillations, but for the most part, the speed doesn't drop. It does not drop like in the solar system. And it, at first glance, wouldn't make sense. If you think about only the light emitting matter, you'd say, well, as I go up further, I'm not enclosing more mass, so why would the speed be the same? The answer is that you are enclosing more mass as you go outward. It's just not the normal matter that you're used to. Instead, it's the dark matter. And so this is the first hint of the existence of dark matter that we will talk about here, the first bit of evidence. Now, if you write down F equals ma, and for a, you use the centripetal acceleration, v squared over r, and you solve for the mass enclosed inside a circular orbit, you get that the mass enclosed is rv squared over g. So here's an equation which, if you measure the radius of the orbit and the speed at which something is orbiting, you can plug it in on the right-hand side and calculate the enclosed mass. And we'll let this interactive figure do the work for us. And so I'll start by just taking a small little region and enclosing just a small amount of mass. And so when I don't choose too large of a radius, I don't enclose that much mass. If I choose a bigger region, larger radius, I enclose more mass. And let's do it again. I'll choose a larger radius still. I'll measure the velocity of the objects at the edge of that radius. I'll plug into the math equation, and I get a larger mass enclosed still. And I could go all the way out to the edge of the observable galaxy and enclose the mass. Now here's where it gets interesting. You keep going out further, like I said before, and you enclose more and more mass. You got to find some kind of gas cloud out there where you can measure its speed at that large radius. But look at how much the mass increases here. If you go out twice as far, you're enclosing pretty much twice as much mass, approximately, in this particular example. And so that is the evidence of this dark matter. The dark matter permeates the galaxy where you see the light, and also the halo where there's not as much light. So it turns out that within our sun's orbit, there's about 10 to the 11 solar masses of material. We do that by a calculation similar to the one that we just talked about on the last slide. Within the galaxy as a whole, the Milky Way galaxy, there's about 1 trillion solar masses. And the vast majority of that is in dark matter. Here you can see the luminous matter, the light-emitting matter, and the dark matter encompasses more than just that region. So Vera Rubin became famous for studying spiral galaxies and their rotation curves. She passed away just a few years ago on Christmas Day in 2016. I had the pleasure to hear her talk once when I was at Vassar College. And many people thought that she should have won the Nobel Prize for the work that we're about to discuss. Right? This was the first clear evidence for the existence of dark matter. And so, what is it? Imagine you're looking at a spiral galaxy, and you could observe different portions of it, portions A and B and C. Now, the light coming from portion B, maybe you're looking at a particular line coming from that spectrum of portion B, and there the line is being represented. That line will be shifted a little bit because the galaxy is moving away from us, right, as the universe expands. Now, if you go over to position C, there, that side, the right side of the galaxy, is spinning away from us. So in addition to the galaxy as a whole moving, there's the additional contribution of the stars moving away from us. And so light from that side of the galaxy will be red-shifted even more than it was from the center. So you see how the spectrum for C has the line red-shifted over to even longer wavelengths. Likewise, if you look at position A, that has a contribution of the stars moving toward us a little bit. So relative to stars in the center of the galaxy, that light from A is going to be blue-shifted a little bit. It's going to be compressed in terms of the wavelengths of light that we see from it. And so by seeing how much the light is red and blue shifted on each side, Vera Rubin and collaborators are able to determine how quickly the galaxy is rotating at different radii as you work your way outward from the center of the galaxy. And in doing so, they build up light curves like are shown here. And these look very much like the light curve we were just talking about with the interactive figure, where they increase at first, and then they plateau and maybe oscillate around a little bit, extending out for hundreds of thousands of light years. This is 200,000 light years at the right edge of this graph. So what she was looking at there was the 21 centimeter line of hydrogen. That corresponds to light that's emitted when an electron in a ground state of a hydrogen atom makes a spin flip. It's this long wavelength of light that we've briefly mentioned before. So here's a thought question for you. What would you conclude about a galaxy whose rotation velocity steadily increases with distance beyond the visible part of the disk? A, its mass is concentrated at the center. B, it rotates like the solar system. C, it's especially rich in dark matter. D, it's just like the Milky Way. Go ahead and pause it if you need to. Well, the answer here is not that the mass is concentrated at the center or that it rotates just like the solar system. Those two answers are actually the same kind of idea. They would result in a rotation curve which is large in the middle and then decreases as you get further and further away, like the first rotation curve that we looked at in this chapter. And D, it's just like the Milky Way. No, the Milky Way and other spirals like Vera Rubin studied, they come up and they plateau and maybe oscillate a little bit, but are more or less flat. If instead, as described in this thought question, the curve goes up and keeps going up, 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 then the reason for that might be that you have more matter. And as you go out further and further, there's a lot of dark matter, which is gravitationally pulling in on whatever's orbiting, and that gives it those increasingly larger orbital speeds. Now, we've mostly up until this point talked about spiral galaxies, but you can do a similar thing with elliptical galaxies as well. Let's say that you're looking at an absorption line from elliptical galaxies. And if you have a lot of slow motion for the stars in this particular elliptical galaxy, well, then there's not going to be a lot of broadening of the line. Some of the stars will be moving more towards you. Some of them might be moving more away from you than the average. But because the stars are moving slowly in this elliptical galaxy, there's not going to be a lot of blue or red shifting. And so the line won't get spread out that much. In contrast, imagine you had an elliptical galaxy where stars are flying all the heck around real fast. Some of them are going to get their light blue shifted a lot more than the average. Others are going to get their light red shifted a lot more than the average. And so if instead of having a really sharp line, that line is going to be spread out, because those stars where the light is red shifted will pull it to the longer wavelengths, and those stars where the light is blue shifted, it'll pull that line to the shorter wavelengths, and you get something like down at the bottom here. So by the width of the absorption line, you get information about how quickly the stars are moving. And that's what you really need to figure out what the dark matter or total matter concentration is. Right? The faster these stars are moving in their orbits, the more mass there must be holding them in those orbits. And what you find is that you get comparable amounts of dark matter in elliptical galaxies as to what you had found in spiral galaxies. Now, Fritz Zwicky, he's an interesting individual. Beautiful picture of him from your reading for today at the beginning of chapter 18. He had a lot of crazy ideas, at least they seemed to be crazy at the time, but many of them turned out to be spot on. And he pointed out some additional evidence for the existence of dark matter in clusters. Up until this point, we've been talking about stars moving around inside of galaxies. Now we're going to talk about galaxies themselves moving around inside of galaxy clusters. And what he noticed was that these galaxies were flying quickly around in these clusters, moving in all different directions. But at the great speeds they had, there must be, Zwicky realized, a lot of matter holding them in place. Otherwise, the cluster would have disintegrated or dissipated by now. At the speeds these galaxies are moving at, if there weren't a lot of dark matter holding them in place, they would have just flown off to large separations and no longer be associated with the same cluster. So you might wonder, how much mass is necessary to hold these galaxies within their cluster as they move around? Well, if you just take into account how much mass there is in stars, you have too little by about a factor of 50. In other words, you need significantly more mass than what's just in the stars. And most of that mass is in the form of dark matter. In other words, the dark matter is much more prevalent, much more prominent than the regular matter. Now here's yet another piece of information providing evidence for the existence of dark matter. What we're looking at here is superposed on a visible image in the background, an X-ray image in the blue and purple here. This photograph is about 8 mega light years across. A mega, remember, means a million. And a typical galaxy like a Milky Way is only 100,000 light years across. So this spans the size of many galaxies, and in fact you can see them clustered here in this particular image. And what we're looking at is this low density but very hot intergalactic gas. The temperature of this gas is hot. That's why it emits in the X-ray. Remember, X-ray is a very short wavelength radiation. And the reason that this is proof for the existence of dark matter is this really hot X-ray emitting gas would dissipate if there weren't enough mass to hold it in place, right? Imagine you have a hot blob of gas. What it likes to do is expand unless something's pulling it back, unless gravity is pulling it back. And if you only accounted for the mass of what you can see, the galaxies and the stars and gas clouds within them particularly, then this gas cloud here emitting the X-rays would have expanded and dissipated and cooled. But the fact that it's there allows us a way to measure how much dark matter there is. In the end, there's about 85% dark matter. 13% of this is in hot gas, regular gas like gas clouds, and 2% of the matter is in stars. Okay, we've talked about a few different techniques for measuring how much dark matter there is, and a few different, therefore, pieces of evidence for the existence of dark matter. Here's yet another one. It has to do with gravitational lensing. So in gravitational lensing, light passes by a gravitational source, and it bends as a result. So imagine that this is you here on Earth, and you are looking at some faraway galaxy that happens to be behind this cluster of galaxies. And the light from that faraway galaxy could kind of pass through the middle of the cluster and you would see it. But what can also happen is the light from that same galaxy comes off in some other direction, but then that path of light is gravitationally lensed, it's curved back toward the Earth. And so you see the light coming from a different direction in the sky, off to the left here in this case. Or maybe the light had gone this way and curved around, and you see another image of the galaxy off to the right. In fact, in this image that we're seeing here, exactly that is happening. These yellowish galaxies, orangish yellow, are foreground cluster galaxies. And then far away in the background, you see this blue galaxy? That's a galaxy, a single galaxy that we're seeing multiple images of. Sometimes the light came this way and bent around towards us. Other times it came this way and bent around towards us. And so we're seeing different images of the same galaxy. If a supernova were to go off in that faraway galaxy, you would see it go off in all of the images. Not all at the same time, because each path might have a different light travel time. It may differ by as much as years. So you might see the supernova go off in one, and then a year later see the supernova go off in a different image. But it is the same galaxy viewed from different angles because of the different paths that the light travel. I picked out a couple different YouTube videos to help to explain this to us. So let's go ahead and transition over to that. Here's the first one, and it was a simulation that was made by Frank Summers a number of years ago now. And it just shows you what it would look like if you had a gravitational lens passing in front of what you were looking at. It distorts and actually brightens as it concentrates the light from the objects behind it. And the second YouTube video that I wanted to show you is this one. Here you are, you imagine you're on Earth and you're looking at this galaxy far away. And if there's nothing between you and the galaxy, you see what you see, an image of the galaxy. If there is this dark matter in large concentrations and a cluster of galaxies between you and it, then that light will be lensed. And here you can actually see that object, that faraway object, as it's distorted and stretched out. You see it along those arcs that surround the cluster. So gravitational lensing also shows us how much mass there must be to bend that light. And if you do the calculation, what you find is that there's much more matter in the region than what can be explained by the light-emitting stars and gas clouds. So here's a thought question for you. Which of these measurements does not tell us the total mass of a cluster of galaxies? A, if you measure the velocity of cluster galaxies. B, you measure the total mass of the cluster's stars. C, you measure the temperature of its hot gas. D, you measure the distorted images of background galaxies. Okay, go ahead and pause it there if you need to. Okay, let's do this. Okay, so the answer is not A. That's the technique Fritz Zwicky used to measure how quickly galaxies were moving within clusters. It's not C, because that's what we talked about with that hot intergalactic gas, and the higher the temperature, the more mass must be holding that gas in place. It's not D, because as we just talked about, looking at gravitational lensing tells you how much mass the lens must have, and therefore it doesn't matter what kind of material the lens is made of. You'll be measuring its mass. It could be dark matter. The answer here is B, that if you measure the total mass of a cluster's stars, that's not telling you the total mass in the cluster of galaxies, because there could very well be contributions from dark matter, important contributions. So all these various methods that we've been talking about, rotation curves of galaxies, orbits of galaxies within clusters, hot gas in clusters, gravitational lensing, they're all indicating similar amounts of dark matter. And that's nice. It gives you more confidence in the existence of dark matter when these independent techniques all give similar results. The dark matter evidence from the bullet cluster we talked about a little bit today with the astronomy picture of the day. And here are those images again, but broken up for us a little differently. We've separated the visual image on the top from the hot X-ray emitting gas image on the bottom. And the green contours here are showing us where the mass is concentrated as determined by gravitational lensing. And so if you look, there's a cluster of galaxies over here in the visual image. Here you see a cluster. And we know that they must have passed through one another at some point in the past, giving these shock fronts that you see. But look what happens. The matter moved right along with the galaxies itself. But the gas collided. Gas from the cluster A collided with gas from cluster B, and it kind of was left behind in the process. This tells us something about what dark matter behaves like. That it doesn't behave like ordinary matter, but rather it can pass through itself and pass through ordinary matter. There are dark matter detectors that exist. People are trying to detect dark matter particles. As of now, it has not been done yet. So what we see, the evidence for dark matter to date, is indirect through its gravitational influences, not direct in that we've actually detected the particles. So given that we haven't directly detected them, you can legitimately ask, does dark matter exist? And there are two options here. One is that it does exist and we're observing its influences. Another option is that we have a flawed understanding of gravity, and that maybe gravity on large length scales behaves differently than what we expect, than what's described by general relativity. And although that's a possibility, most astronomers would tend toward option number one here, that this dark matter is something real that we are detecting its influences of. And you might ask then, okay, well, what is it? There were in the past two possibilities for what dark matter was made up of, the machos and the WIMPS. And by the way, that'll be the answer to today's reading quiz. Machos and WIMPS. Here's how you spell machos, and here's how you spell WIMPS. Now, MACHO stands for Massive Compact Halo Objects. A compact halo object would be, like the name describes, something like a black hole or white dwarf or neutron star, very compact, massive, and in the halo of galaxies. And if you had enough of these swarming around, that could contribute significantly to the mass in the universe. Now, we now know that dark matter cannot be explained by machos. Machos do exist, but not nearly in the numbers that you need to describe how much dark matter is out there. We know they exist because of gravitational microlensing. Let's say you're looking at the Large Magellanic Cloud, for example, and a black hole happens to pass between you and it. Somewhere in the halo of our galaxy, a black hole happens to be lined up with the Large Magellanic Cloud, and you see it gravitationally lensed, the LMC, as a result. And so you monitor the LMC and other objects for this lensing, and they do occur, but not enough that you can explain all of dark matter. The WIMPS explanation is much more likely. It's the better bet. It's the best bet that we have out there. WIMPS stands for Weakly Interacting Massive Particles. We've talked about weakly interacting particles before. The neutrino, remember, it's created in fusion processes and it streams right on out through the sun, rarely interacts with matter and so on. Well, that's a weakly interacting particle. It's just not massive. It has a very, very low mass, right? Not large enough of a mass to explain the existence of dark matter. However, these neutrinos may have cousins that are much heavier. And these heavy cousins, the WIMPs, the weakly interacting massive particles, they're expected to exist. They have some nice side effects, like they help explain why galaxies can collapse down and form as quickly as they do. And they would be presumably massive enough then to explain the dark matter. So these are heavy neutrino-like particles that are thought likely to exist. So that's what I wanted to talk about today. What we're going to do next is review the new constellations with some slides. These are the constellations that I promise you will be on your final exam. They're also fun to learn about because you'll now have something to look for in the summer sky. Once we've looked through a few slides on those constellations, we'll go ahead and launch Stellarium, and I'll quickly review all the constellations and stars and other objects within them from the semester. Because on the final exam, although I promise you I'll be asking you the summer stars and constellations, I will be asking you about a smattering of other things. And so let's go ahead and do that now. Here's the summer triangle, and this shows us the objects that I'd like you to learn about. In addition, I'd like you to learn that in the Lyra the Harp constellation, down between these two bottom stars here, there's the Ring Nebula. It's a planetary nebula. But this is Lyra the Harp. You look for this triangle and then this squished rectangle. Vega is the brightest star and one of the corners of the triangle. The brightest star in Cygnus the Swan is Deneb, and I'd like you to learn that. Here's the body of the swan and the wings of the swan, and Cygnus flies right along the plane of the Milky Way galaxy. It turns out that right in the middle of Cygnus the Swan, there's Cygnus X1. We talked about that black hole that has a mass of about 15 to 20 times the mass of the Sun. But I'm asking you to learn about Deneb in Cygnus the Swan. And then finally, we have Aquila the Eagle. And Altair is the brightest star in Aquila the Eagle. And together, Altair and Vega and Deneb, they make up the summer triangle. So this is, which constellation? Say it. Lyra the Harp. You can also say Lyra the Harp if you want. Now, the square down here represents the Ring Nebula. That's a planetary nebula. Remember what's at the center of planetary nebulae? White dwarfs. They were the cores of those stars. Once those stars blew off their outer layers to make the planetary nebula, the core that's revealed in the center we now call a white dwarf. And this star up at the top here, that is Vega, the brightest star in the Lyra the Harp constellation. Now, which bird do you think this is? Cygnus the Swan or Aquila the Eagle? It's Aquila the Eagle. There it is. And the bright star in Aquila the Eagle is known as Altair. And you look for this egg-shaped pattern of stars that make up Aquila the Eagle. And finally, this is Cygnus the Swan. Now, if you've studied biology, you may know that a cygnet is a baby swan. And if you knew that, that may help you to remember Cygnus the Swan. Or if you didn't know that and you remember Cygnus the Swan, that might help you to remember that a cygnet is a baby swan. Now, the other name that the Cygnus the Swan constellation goes by is the Northern Cross, because it kind of looks like a cross. Here's what would be typically the vertical part of the cross and the horizontal part of the cross. There is also a Southern Cross, but you need to see it from the southern hemisphere. This bright star in the tail of the swan, and in fact that's what this name translates as, is Deneb, the tail of the swan. Alright, for the stellarium portion I made a separate standalone video. This will help you study the constellations that we've been learning about all year, including these most recent ones for the summer constellations. So there's a link right up here, how to find the constellations in the sky, Taurus, Gemini, Cancer, Leo, Virgo, Lyra, Bears, and more. That's the one that you're going to want to click on to review those constellations. I hope you're all doing well. Take care. Stay safe.